Okay, so I'm gonna try this again. About the fourth time I've done it, but that's okay. So the PowerPoint that I loaded up on Blackboard to be a little bit different than this. I had to edit this a little bit. So if you look at the PowerPoint on Blackboard, it'll be a little bit different, but hopefully you'll see how it follow. Be very similar. All right, so we're going to talk about buffers now. And what buffers do is they resist change to pH. So often you want to do is you want to have a solution that stays, the pH stays very constant, and making a buffer is a way to do that. And the way you make a buffer is you take two parts. One part is going to be there'll be two kinds you can do this. So let's say you want to keep a low pH, like a pH of 4.2 or something. You would use a weak acid and conjugate base. It's conjugate base. For instance, you might use acetic acid and sodium acetate. Sodium acetate's a solid, but when you put it in the water, it dissolves and it produces acetate, which is the conjugate base. If let's say you want to have a higher pH, to like pH 8 or something, then you would make a base buffer, and you might take ammonia and its conjugate acid. All right, why buffer is important? Especially in biology. And you have, for instance, in your blood, you have blood buffers. And what the blood buffers do is they keep the pH at a fairly constant pH around 7.35, I believe it is. And if the pH goes up or down too much lower than this, then they can really disrupt how your all the chemical reactions that take place in your blood, and you could have serious problems with this, kill you. Also, enzymes in your body need to have constant pH, and so because enzymes have optimal pH, and so your body will produce natural buffers that keep the pH of at a very narrow range for enzymes. Okay, how do they work? Well, let's take a look at. Let's say we want to have a lower pH, like pH 4 or whatever, and so we're going to make an acid buffer. So let's say you take a weak acid, HA, H, and whatever A is, and then it forms a conjugate base A minus. So what it has to do is be able to. What you would like it to do is neutralize a strong acid, strong base. So what that means, you're going to have both of these in significant amounts, so that they can really be strong, really concentrated, so that they can absorb any kind of strong acid or strong base. So what happens is, let's say you add acid, some kind of H plus from like nitric acid. So what's going to happen is the conjugate acid is going to grab a hold of the H of the acid, and it's going to make more of your weak acid. So it absorbs H plus as though it wasn't even put in this solution, and the pH will stay very constant, and there will not be a buildup of H plus. So if you go the other way, if you add more OH minus, what it'll do is combine with the acid and form more conjugate base. And so OH, which increases the pH, would be absorbed, and therefore no increase in pH. So a specific example would be acetic acid and acetate buffer. So the acetic acid dissociates into acetate and H plus. And so let's see what happens. So let's say that you add some base to this guy. So this reaction. So what's going to happen is the OH is going to react with the acid, and when it does that, it'll force the reaction to the right, and what it'll do is form more of the base. Okay, so essentially knocking this guy out. Okay, now if you add acid, so if you add more acid in here, So if you add more H plus, what it's going to do is going to drive the reaction to the left. Let's Shockley-Hayes principle. More of H will drive the reaction to the left, and what it'll do is combine with the conjugate base, forming more acid and removing the H plus and keeping the pH constant. All right, so let's look at a specific example. Let's say I have 0.55 molar acetic acid for the Ka of 1.8 times 10 to the minus fifth, and it's added to 0.45 molar sodium acetate. What is the pH of this solution? Okay, so what we're going to need is the Ka of acetic acid, 1.8 times 10 to the minus fifth. And this is the equilibrium expression. All right, when you put sodium acetate into water, again, the sodium splits off from the acetate. So what you do is you have 0.45 acetate and 0.55 acetic acid. So let's set up an ice table and see what happens here. So your starting concentration is 0.55 acetic acid, 0.45 molar acetate, no H plus. Okay, now the reaction is going to go to the right, and that's because if you figure out the Q of this reaction, so the Q is going to be the basically equilibrium expression, but not at equilibrium, so it's going to be 0.45 times 0 over 0.55. If the Q is less than K, the reaction will move to the right. If it was greater, move to the left. So you can see 0.45 times 0 divided by 0.55 is equal to 0, which is less than the K, and so the reaction is going to move to the right. So that means some of the reactant's going to come off, and you're going to form product. Okay, now the amount that comes off, X, is going to be very small because the ratio of 1.8 times 10 to the minus fifth to 0.55 is very, very large, okay? And so, or small. And so basically there's no effect on this value or this value here. And so we can neglect how they affect the original concentrations of these two. They do affect it, but not within any kind of precision that we want in our calculations. But we definitely formed some new H plus, and that's what we want to find. Okay, so what we do is we use Ka expression as Ka equals product over reactant. So it's going to be X times 0.45 over 0.55 equals 1.8 times 10 to the minus fifth. Okay, and then rearrange the equation, and then you get X equals this, and you get X is equal to 2.2 times 10 to the minus fifth molar. Then figure out the pH at 4.66. Okay, so notice, one thing to notice is that X has the change in the X has no effect, negligible effect on the amount of base and acid. Okay, we're going to use this problem again, like in slide number 20. So we're going to use the same numbers. So just be aware of that when we get to it. All right, so let's say I want to figure out the pH of a buffer solution. That's 0.25 molar benzoic acid and 0.6 molar sodium benzoate. The Ka is 6.3 times 10 to the minus fifth. Okay, we're going to set it up ice table, and you guys go ahead and try it. If you want to just turn off the presentation here for a minute or two and see if you can do it on your own, and then you come back. All right, so set up the ice table. Okay, the reaction moves to right for the same reason we did talk before. Again, for the same reason, you could X is negligible for the concentrations of the acid and the conjugate base. It only affects the H plus. Okay, So the Ka is equal to the benzoic this ion times H plus divided by the amount of acid, and so you get 0.6 times X over 0.25 equals 6.3 times 10 to the minus fifth. Solve for X, and you get it's 2.63 times 10 to the minus fifth. That should be molar. And then the pH is 4.58. pH doesn't have any units. All right, so, okay, so there you go. Okay, there's another possible way to come up with this answer, and it's using this equation here called Henderson-Hasselbalch equation. And we actually used it in one of the labs. It was called determining the pKa and molar mass of a weak acid. And what we did was we you titrated until you figured out that inflection point, and and at the inflection point, the amount of acid is equal to the amount of base. So that means this is going to be 1. So log of 1 is 0. And so pH at that point, pH equals pK plus 0, and pH equals pKa. And so what you can do is you can go over, you would look at the graph, look at the pH, where this happens, and it's the pKa. All right. So that's where we use the equation. But we could also use it on the problem we just did. All right. So we had the Ka of the last equation was 6.3 times 10 to the minus fifth. Take the minus log of that to find out the pKa. Then what we're going to do is just plug it into the Henderson-Hasselbalch equation. So we get pKa, which is 4.2, plus the log of the ratio is 0.6 over 0.25, which is 0.38. Added to 4.2 is 4.58, which is the same answer we got using the ice table. Okay, so let's actually talk about preparing a buffer at a given pH. And so there's a couple things we're going to want to do. We're going to want to figure out what is a good buffer solution to use. And what you want to do is make sure the buffer solution that you use should have a pKa that's within 1 pH unit of your desired pH. And then what we're going to need to do is from that we're going to have to figure out the ratio of the conjugate acid to the conjugate base. Actually, it should be the ratio of the acid to the conjugate base. Okay, and then we can figure out how to make it. Right, so let's say I have a solution that I want to make that keeps constant pH at 3.9. And first of all, I want to know if it's okay to use formic acid and formate. So I'll look up the pKa of formic acid, and it's 3.74. And I can see that it's within 1 pH unit of my desired pH. So it's okay to use formic acid formate buffer. Okay, so what I'm going to do is figure out the ratios of my acid to base. All right, so I take the Henderson-Hasselbalch equation, rearrange it, and so I got pH minus pK equals the log of my ratio. This I'm going to want to get this value here, my ratio, and then plug in my pKa's and pH, and I get 3.9 minus 3.74 equals log. If you take the anti-log, both sides, you get the ratio is equal to 1.4, and then the amount of acid, the amount of base is equal to 1.4 times the amount of acid. So we got to make sure that this is the proper ratio. Okay, so let's say I want to make a 0.5 molar solution, 2 liters of a total concentration 0.5 molar. So my So my total concentration is going to be the concentration of my acid plus the concentration of my base. So X is the concentration of the acid, Y is concentration of the conjugate base. And I know from what we just found is that the amount of the ratio of base to acid is there's the amount of base is there's 1.4 times 10 to the minus 10. It's 1.4 times the amount of acid equals the amount of base. So what I'm going to do is take the original equation, this guy up here, and substitute this into here. Okay, so what I'm going to do is I'm going to substitute this value here for this. So instead of having this value, I replace it with this value. And I keep this, and so I have this plus this, so 1 plus 1.4 is 2.4 times the amount of acid. So 0.5 equals 2.4 the amount of acid. Solve for X, and X equals 0.21 molar acid. And then to figure out how much base, you just multiply the 0.21 times 1.4, and you get 0.29 molar base. Okay, so now let's actually figure out how we're going to make this up. Okay, first of all, the acetate is going to come from sodium acetate. So you're going to have to figure out how many moles of, not acetate, formate, I keep on calling it acetate. This is formic acid and formate, not acetic acid and acetate. So, you know the moles of formate is equal to, you want the rate the molarity to be 0.29 moles per liter. Okay, you need 2 liters, so you're going to definitely so you need to do it twice, and so you're going to need 0.5 moles of formate. Well, the formate is going to come from sodium formate, and for every 1 mole of sodium formate, 1 mole of formate is found. Right, so what you just need to do is measure out 0.5 moles of sodium formate, and that will give you 0.58 moles of formate. Okay, so you can measure this out. All right, so you get a jar of it. All right, so we need to figure out, so the molar mass of sodium formate is 68 grams per mole. You need 0.58 moles of it, so multiply by 68, and so you're going to need 39.54 grams of sodium formate, and that will give you your proper moles of formate. Okay, so what you do is you go ahead and measure out 39.44 grams of sodium formate. All right. The next thing you do is the formic acid is going to be in a solution, a 10 molar solution. And what I'm going to have to do is I'm going to have to dilute the 10 molar solution to give me the right final concentration. So I want to have a solution that's 0.21 molar. Okay, so what I'm going to do is use the dilution formula to find out how much 10 molar formic acid to make the solution. All right, so here's your dilution formula. The concentration of your stock times the volume of the stock equals the concentration of your final solution times the volume of your final solution. And what we want to do is find out the amount of stock of the 10 molar we need to add into the 2 liters to give you the proper concentration. So just rearrange the equation, you get this. So So the volume of the stock equals 0.21 molar times 2,000 mils, so I changed the 2 liters to mils, divided by 10 molar, and the answer is 42 mils of 10 mole formic acid. So the way that you would do this, so you want to get a solution that's 2 liters, and we made up solutions before. So what I would do is I'd take, we get like a 1 liter beaker, and I'd fill her up to about 800 mils, and then I'd weigh out 39.44 grams of sodium formate, mix it in with the 800 mils of water or so. It doesn't have to be exactly 800 mils. And then measure out 42 mils of the 10 molar formic acid, add that, also to 800 mils. Transfer that to a 2 liter volumetric flask, and then bring the final volume up to 2 liters. Okay, and that would give you your desired solution. Okay, so buffer capacity. Alright, defined as a mole's strong acid base that cause pH of 1 liter to change by 1 pH unit. Alright, and we're not going to do a buffer capacity problem here, but that's what you would need to do. Instead, what we're going to look at is an extra scenario. So let's say we add some base or acid to a buffer, and so let's see what happens to the pH after we add the base or buffer. Alright, so this is first going back to the problem I talked about, slide 7, where you have 0.55 molar acetic acid and 0.45 sodium acetate. And what I want to do is find out what is the pH going to be after I add 0.06 moles of hydroxide ion. Is it going to change the pH all that much? Okay. All right. So the first thing you do is let's go back to the original table. The original table, we found out that solution had a pH of 4.66 with the amount of acid being 2.2 times 10 to the minus fifth molar. All right. Okay, so and also what we're going to need is, since we're talking about moles here, we need to have everything in moles. And then when we need to change it back to molarity, we can. All right, so first of all, we're going to look at what happens when you add the hydroxide to the acid. All right, so what's going to happen is acid is going to absorb the hydroxide to form more of the conjugate base. So let's write out the ice table here. So you start out with 0.55, you add 0.06 and to 0.45. All right, so what after you add that 0.06, what's going to do is it's going to be absorbed by the acid. So this is going to decrease by 0.06. This is going to go down by 0.06. It's going to go all the way, okay? And then what you're going to do is you're going to make more base. So after you add this amount of base, you will have 0.49 moles of your acid and 0.51 moles of your base. All right, so now let's calculate the new pH. All right, so now you have 0.49 of your acid, 0.51 of your base. And so what's going to happen is, again, you're going to decrease the amount of X, and this increase by X, and there's going to be basically no effect on the acid or base, and you get a new pH. And that's what we're going to find out now. So just plug in numbers in, so the H plus equals 0.51 over 0.549 equals 1.8 times 10 to the minus fifth, and now the H plus is 1.73 times 10 to the minus fifth, and you can see here that now the pH is 4.76, and it's gone up by changed by going up by 0.1, which is a whole lot. Now it does change, but let's see if we didn't have the buffer there. So if you didn't add the buffer, so if you just added 0.6 moles of hydroxide to pure water, the amount of base would be 0.06, that the PO would be 1.22, the pH would be 12.78. So the pH would change by almost 6 pH units, which is 10 to the 6th, almost a million times more basic than when you started. Okay, so what the buffer did, the pH only went up by 0.1, which is about 100 times, not 100 times, yeah, it's like 1 times or less than than you started out with. Okay, so buffers do a really good job of keeping the pH constant.